All right, so this is part 2 of the fundamental theorem of calculus. And essentially in part 1, we looked at the idea that you can think of the process of integrating and the process of differentiating as being inverse processes of one another. And so in essence, you can think of a derivative as kind of canceling out the effect of an integral in a sense. And so with that said, the second part of the fundamental theorem of calculus allows us to actually evaluate these definite integrals without just finding the areas of various shapes. And here it is right here, and it's actually quite nicely pleasant and kind of elegant that the integral of some function from a to b, which remember represents the area under the curve from these bounds of a to b of some function, is the same as finding the antiderivative of that function at b minus the antiderivative of that function at a. And this is always true as long as the function is continuous on this interval, and again assuming the notation that, again, this is the antiderivative of this. If a function is not continuous on that interval from a to b, then all bets are off. All right. But if we have a continuous function, and you want to find the integral from a to b, it's the same as finding the antiderivative at those points. And this whole kind of chapter starts to come kind of full circle back to antiderivatives. With that said, let's try it. Here is a function, and again, the equation you see, the graph you see here is the graph of 4 minus x times root x. And I want to find that shaded region, which we can see is from 0 to 4. And that matches up with the integral we see here. All right, so how do I find the area of that region? Because I can't, it's not a circle. It's, I can't just use a basic area formula from previous grades. I can use the fundamental theorem of calculus. And so first I need to find the antiderivative of this. And so that's actually going to be a lot of my work, just finding the antiderivative of 4 minus x times root x. First things I would do, I'm going to call that just f of x. Let's just call it f of x. So before I find the antiderivative, just like if I was differentiating, I would actually prefer to distribute this root x and think of it as x to the 1/2. So I have 4 times x to the 1/2 minus x to the 3/2. And so I'll call that f of x. And so now I want to find the antiderivative. So the usual notation is capital F of x. And I can just use my power rule backwards. I have 4 times 1/2 plus 1, so 3/2. Oh, sorry, that's wrong. Take that back. I have 4 times the reciprocal of 1/2 plus 1, so that's 2/3, times x to the 1/2 plus 1, so 3/2. And then minus, again, I have the reciprocal of 1 more than 3/2, so 2/5, times x to 1 more than 3/2. There's my antiderivative, which I'll clean up a little bit to 8 over 3x to the 3/2 minus 2/5 x to the 5/2. And so with that being my antiderivative, if I want to find the area of the shaded region, I just need to find the value of this antiderivative at 4, and from that minus the value of that same antiderivative at 0. And so for this case, I'll write it formally like this. Therefore, the integral from 0 to 4, I'll just call it f of x dx, is going to be the same as f at 4, big F at 4 minus big F at 0, which in this case is 8/3 4 times 4 to the 3/2 minus 2/5 times 4 to the 5/2, and all of that is f at 4 minus, same idea with 0. The good thing is I can see already when I replace x with 0, my antiderivative is 0, but I'll be complete. I'll write in the 0 here, which is kind of silly, I guess. All right, so that corresponds to these two antiderivatives. And at this point, if you perform some calculations, all of this right here becomes 64. In fact, it all simplifies down to 128 over 15 minus 0. And so 128 over 15 is my answer. All right, so notice if I just kind of look back, that value of 128 over 15 is the exact area of that region that's been shaded. And, you know, about half of my work was working with the antiderivative. Half it was getting to a point before I could find the antiderivative. All right, so let's look at this one. I want to find the area of that shaded region. And the graph you see here in red is the graph of 1 over x squared. And I'll call this f of x for the sake of my work. And so I'm going to make a mistake. So I will say what I'm going to start doing now is deliberate, but I wouldn't write it down. Or if you are going to write it down, fair enough. I'm writing it down, but it's going to be wrong. Okay, so I'm going to call f of x 1 over x squared. Okay, which I can also call x to the negative 2. And for the purpose of finding an antiderivative, I'd rather deal with x to the negative 2. So let me find my antiderivative. Using my power rule backwards, I add 1 to negative 2 to get negative 1, and divide by negative 1, same as just multiplying by negative 1. So really I have just that as my antiderivative. That's quite pleasant, which again is equivalent to just negative 1 over x. Okay, and so if I want to find this integral, you may think, and again, I may have made the mistake already. It may come up very soon. If I want to find the integral from negative 1 to 3 of this function f of x dx, it's going to be the same as f at, 3 minus f at 1. And function f, again, is pretty simple. So in this case, I have negative 1 over 3 minus negative 1 over 1, which is negative 1/3 plus 1. Sorry, hold on. Again, oh, that's a mistake, yes. It's from negative 1. There we go. That should be a negative 1 right there. Although, just to confuse you, that's not the mistake I was talking about. But anyways, going back, I just wrote down the wrong number there. So this, when you put negative 1 into the antiderivative, you get minus just 1. And so negative 1/3 minus 1 is negative 4/3. And I know that cannot be correct. How do I know that cannot be correct? Just look at the graph. A negative area, a negative integral is fine. But if I look at this graph, that's all positive. That shaded region is definitely, there's nothing negative about it. This cannot be correct. Plus, 4/3 sounds pretty small. That's like negative 1 1/3. And you know, there's a full square right there. There's another full square right there. This cannot be correct. And so, why is this incorrect? Because I am not using the fundamental theorem of calculus properly. If we go back here, this is always true if and always when a function is continuous on this interval. But if we look at the question I have, it is not continuous on the interval from negative 1 to 3. There's clearly that vertical asymptote, which means all this work I've done here is meaningless. And so I can't use this. In fact, I can't get an answer for this, at least not from what we've learned. And so let's make a note. We cannot use this work because 1 over x squared is not continuous. On the interval negative 1 to 3. And if you notice that right away, then there's no point going on. Now I will say, you may assume by looking at this, because there is a vertical asymptote on this function, you may assume, because it goes on forever up, the area must be infinitely large. That could be the case, but that's not an assumption we should make. We will see that it is possible for a function to go on forever, and yet the area under the curve is not infinite. That is definitely possible. It depends on how it approaches infinity. And so, but just from what we have here, I just can't, the answer is definitely not negative 4/3. And so really, I've asked you, we don't have the tools to answer this yet. But again, the main point of this question was, we cannot always use the, if we're going to use the fundamental theorem of calculus, the second part, we got to make sure we're using it properly. Okay, last question. This time I can see the function is definitely continuous. I give you the graph. So I want to find the area of this region from negative pi over 2 to pi. Okay, so definitely I don't have to worry about this function not being continuous. I can see it's continuous. So I want to call this part here cos x times e to the power of sine x. I'm going to call that f of x in terms of finding my antiderivative. Okay, so how do I find my antiderivative? Well, I know the antiderivative of cosine is sine. I know the antiderivative of e to the power of something is itself, but this is e to the power of sine x, not e to the power of x. And plus I'm multiplying these two together. And you may think to yourself, like, well, do we use the product rule? But I'm not differentiating, I'm anti-differentiating. And so we potentially run into a problem. From what we've talked about so far in terms of finding antiderivatives, we haven't directly learned enough to figure this out. Not directly. We've indirectly definitely learned enough. But directly, this, I just can't yet differentiate this just by thinking about a power rule or something. But we've been differentiating for a long time now. And so this antiderivative, whatever it is, must have a derivative equal to cos x times e to the power of sine x. And so right now, our own approach is through inspection, which means kind of intelligent guess and check, I guess, by kind of looking at it and thinking about all the past experience we have working with derivatives and thinking about what function would give a derivative like this. And most likely you make a guess, and then it should be pretty easy to check. And so a guess I would make is that since this does involve e to the power of something, my antiderivative must also involve e to the power of, let's see, sine x. Let's just see. Okay? Because I know the derivative of e to the power of sine x will be very, very similar to that. So let's see if this is correct. Okay? I know there has to be e to the power of something at least. And so what's the derivative of e to the power of sine x? Well, the derivative of e to the power of sine x is e to the power of sine x, but then times the derivative of the inside function, in this case the sine of x. I'm using the chain rule. And so the derivative of sine x is cos x. And there you go. That is the derivative of that, which conveniently enough matches up exactly with what we want. So now I know through a little bit of inspection, or I guess guess and check, but again, it's not a complete guess, it's building on our knowledge, our hopefully extensive knowledge of working with derivatives, that the antiderivative must be e to the power of sine x. Now, what this does, this question as well does, is kind of show really how limited our knowledge so far of antiderivatives is. We have, even though we know the power rule in reverse and a few other things, we don't know much. And think back to differentiating. If all you know is a power rule and a couple of the derivatives, if you don't know how to use the chain rule, for example, and that's what we really use here, the chain rule backwards, things fall apart very, very quickly. And so that is why we need more lessons on integrals. But now, for this question, we've got enough. Okay? I know the antiderivative is e to the power of sine x. And so the integral I'm trying to find is going to be the antiderivative of this at pi minus the antiderivative of this at pi over 2. Now, one way of showing that without actually writing out this whole integral again, and one common way is put kind of square brackets around here, because really this is what I'm going to work with now, this e to the power of sine x, and just show the bounds with a little negative pi over 2 down here and pi up here. Because really this is what I'm focusing on. All right, and so with that said, what does this equal? Well, this equals e to the, my marker got very thick suddenly. Take 2. What does this equal? This equals e to the power of the sine at pi minus e to the power of sine of minus pi over 2. So I'm just about done. What is the sine of pi? The sine of pi is 0, right? If we think back to our angles in standard position for the sine function starts at 0, goes up to 1, goes back down to 0, goes down to negative 1, and on and on and on. Minus, what's the sine of minus pi over 2? minus pi over 2 is this angle going 90 degrees backwards. And I can see from what I've drawn already, the sine of minus pi over 2 is negative 1. So e to the negative 1. And so cleaning this up, e to the power of 0 is 1 minus, and this is a great answer. That said, I kind of like this one better as well, just because, I don't know, I do. There's that area. And so notice, if we can find our antiderivative fairly pleasantly, then we can find these exact areas quite quickly. Our hurdle may be, what if we can't find our antiderivative so easily? But that's where we're done.